Hey everyone, welcome back to Wirelesspro. Today, we're diving into one of the most exciting frontiers in wireless communication, neural receivers. As wireless systems evolve into 5G and 6G, the complexity of signal environments is exploding. We're talking about high mobility, dense urban deployments, massive MIMO, and unpredictable interference. Traditional receivers, built on decades of mathematical modeling, are starting to hit their limits. They rely on fixed algorithms and assumptions that don't always hold up in the real world. So here's the big idea. What if we could teach a receiver to learn how to decode signals? In this video, we'll explore how neural receivers are transforming signal processing from rigid pipelines to flexible, learning-driven systems. We'll walk through the architecture, training, and performance of these AI-powered receivers and how they're reshaping the future of wireless. Let's jump in. Let's start with the real-world challenge. Imagine a dense urban environment, multiple users moving at high speeds, signals bouncing off buildings, and base stations firing off beams in every direction. This is the world of massive MIMO, where dozens of antennas serve multiple users simultaneously. It's powerful, but it's also chaotic. Doppler shifts distort the signal. Multipath propagation creates interference, and pilot signals? They're sparse and often overwhelmed. Traditional receivers rely on carefully placed pilots and handcrafted models to estimate the channel. But in environments like this, those models start to break down. Neural receivers offer a new approach. They learn directly from the data, adapting to complexity, generalizing across scenarios, and decoding signals even when traditional methods fail. This is the challenge. And it's exactly where neural receivers shine. Let's rewind and look at how signal processing used to work. On the transmit side, we go from bits to waveforms through a series of modular blocks: source encoding, rate matching, symbol mapping, precoding, and OFDM modulation. On the receive side, we reverse the process, starting with FFT and synchronization, followed by channel estimation, equalization, demapping, and decoding. Each block is carefully engineered, but also rigid and assumption-heavy. Now imagine replacing that entire receiver chain, from FFT output to decoded bits, with a single neural network. Instead of estimating the channel and tweaking filters, the network learns to decode directly from the received signal grid. It's like giving your receiver a brain and letting it figure things out on its own. This shift, from modular blocks to end-to-end learning, opens the door to more adaptive, robust, and scalable signal processing. So how do we build this brain? We start with a deep convolutional neural network, stacked with residual blocks to help it learn complex patterns. Residual connections allow gradients to flow more easily during training, making it possible to build deeper and more expressive models. Then we add dilated convolutions to expand the receptive field. This lets the network capture long-range dependencies in time and frequency, without increasing the number of parameters. And finally, we use depth-wise separable convolutions to keep things lightweight and fast. These break down standard convolutions into two steps: depth-wise filtering and point-wise projection. The result? A neural receiver that's smart, efficient, and ready for real-time signal decoding. This architecture is designed to handle the full resource grid and extract meaningful features that represent the transmitted bits. Let's peek inside the neural receiver. The input is a time-frequency grid formed by post-DFT samples across OFDM symbols and subcarriers. This grid includes received symbols, pilot signals, and optionally initial channel estimates. We also provide noise variance, which varies across batches during training. This helps the network learn to adapt to different channel conditions. The network processes this grid using convolutional layers and outputs log likelihood ratios, or LLRs. These LLRs quantify the confidence of each bit being a 0 or 1. They're passed to an outer decoder, like LDPC, which reconstructs the original message. Importantly, the network computes LLRs for all resource elements, but only the data-carrying ones are used for decoding. This end-to-end learning approach allows the receiver to bypass traditional channel estimation and equalization, learning directly from the signal itself. And because it's trained on diverse channel conditions, it generalizes well, even to scenarios it hasn't seen before. Now let's see how it performs. We ran simulations using the Wirelesspro framework right inside VS Code. The setup? A 5G NR uplink in an urban micro-outdoor scenario, sweeping across SNR values. On the left, we've got BLER versus SNR. The neural receiver consistently beats the traditional one, especially when the signal is weak. On the right, throughput versus SNR shows how much data we can decode. Again, the neural receiver holds its own and often pulls ahead. These results highlight the power of learning-based signal processing. Instead of relying on fixed models and assumptions, the neural receiver adapts to the environment, delivering robust performance across a wide range of conditions. And the best part? It's all reproducible, scalable, and integrated into our Wirelesspro framework. You can generate datasets, train models, and run inference, all in Python, using 3 GPP-compliant configurations. So what did we learn? Neural receivers are changing the way we think about signal processing. They're flexible, adaptive, and built for the chaos of real-world wireless. Whether it's decoding in noisy environments, handling multi-user interference, or scaling to 6G, these receivers are up to the challenge. And with tools like Wirelesspro, you can build, train, and deploy them yourself. This isn't just an upgrade, it's a paradigm shift. Thanks for watching, and if you're into next-gen wireless, try out Wirelesspro now and stay tuned for more AI and research.